In this video, I'll talk about some of the reactions that the acetylide ions can do. So a common acetylide ions would be obviously within a triple bond where I can write down R, C, triple bond, carbon with and a carbon within a negative charge. And a lot of time you may be just using just an acetylene or the anion as an acetylide ion, something like that, because that's the smallest one. But then if you get bigger on the side chain here, that can create the problems in terms of acting as a nucleophile. But for right now, like when you see something like this, I can say that this is going to be in a strong nucleophile, and it's also going to be in a strong base. So I can have this acting as a nucleophile and acting as in a base. It really depends on the situations and the conditions that you're in. And make sure you know how you actually can produce it. So like for example, if I'm using propine for a minute, the propine um, proton can be easily removed if I use a base that's strong enough. And we talked about that, what bases are strong enough to typically remove the alkyne proton. And most of the time you either use NH2 minus or you use H minus, and that makes the NH3. So this is really the anion that you create here, which would be acting as in a base and in a nucleophile. So I'm going to take an example of just in a simple one, the acetylide. So that's in a small, strong base and strong nucleophile. And like I said, if the R carbon chain length gets bigger and bigger, then it may not be able to act as a nucleophile that well, because then it becomes bulky, and in that case, it wouldn't be more likely to act as a base. But suppose I have some of these reactions kind of written down here. So suppose I have this alkyl halide here, and I'm going to go ahead and run this with the smallest acetylide ion here. So this first one here. So this, I know it's in a strong nuke and strong base, but then this is in a primary alkyl halide. So primary alkyl halides with a strong nuke, strong base will primarily do an SN2 mechanism. So this will do in a backside attack here, and this comes out here. So I have this carbon H triple bond carbon, and then I do make a new bond here. So I want to show that within a straight line. And then I got the other guys as CH2 and CH3. So that's your ethyl that you're coming from the primary alkyl halide. That's one way of drawing it, but if I want to just draw it without showing the carbons, I would just do something like on a triple bond here. You make a new bond, and then you would have two carbons um, there, and then obviously this would be considered the new bond here. So that does an SN2. But if I was doing something similar within a secondary alkyl halide, and I was doing, let's say, this guy right there, that's in a strong base, strong nuke within a secondary alkyl halide, then this has a potential to do both SN2 and E2. Primarily, E2 probably going to dominate, but you still get both of them in there. So um, the products that you can get, if I'm trying to draw the SN2 product, which is going to involve the inversion in stereochemistry, I can say that the new bond that you're going to make here when you run the SN2 will be going back in the page, and then I would have this triple bond here, basically. So carbon and triple bonded CH. Or I can just draw a triple bond here as well. Like if you don't want to show it with the carbons, I can just draw it like this. I can just draw a triple bond right here, and that means the same thing. So that would have been your SN2 product, but then your E2 product, this is in a small enough base, it's not in a bulky base, so it will do a Zaitsev. So I would make the major product as the trans alkene here. So trans-butene would be the major product in that case. So that would have been the E2. So this is where you got to be really careful with like what type of alkyl halide you're using. But now suppose if I was using tertiary alkyl halide like this one here, and I have the same thing as an acetylide, so which is in a strong base, strong nucleophile. Within a tertiary alkyl halide, this will primarily do E2 mechanism only. And since it's in a small enough base, it will do an Zaitsev. So I would be creating a double bond right there. So it will be removing if I want to show the mechanism here, it would be removing this anti-hydrogen here. All right, and then this will be coming in there, and that would come out. And we don't have to worry about the E and Z here because one carbon contains the same groups in there. So that's what the product is going to look like. What if I was using something like benzylic halide, like this one right there? So this benzylic halide, suppose I'm running this with acetylide again. Now this benzylic halide can't really do an E2 because you don't really have an beta carbon within the hydrogen. So you do have one beta carbon here, but there's no hydrogen here, so you can't really run an E2. So the only thing you can really do, either an SN1 or an SN2, but since you have a strong nucleophile, that would more likely do an SN2 mechanism. But we don't really have to worry about it because it probably wouldn't really have any stereochemistry involved. So regardless you do SN1 or SN2, it would be making the same product here. So it will end up making something like this. So you would have this attacking right here, doing the backside attack, and then this kind of leaving. And that's how you make that as your product in that particular case. If this was a chiral, then you want to make sure you invert the stereochemistry because you're running in an SN2. How can you make this chiral? So instead of having two hydrogens here, I could possibly have one of them to be deuterium. Like for example, suppose if I'm just going to use the same one on the top there. So suppose go ahead and put this down here. And I'll have this coming out of the page. And I'll have a D here. So when you make the product, what you want to do is you want to kind of leave everything else the same because this is an SN2 mechanism. D just isn't a deuterium and heavier isotopes. It's an inverted stereochemistry. So when you draw this, I can draw this going back in the page. And that's pretty much it. But if it's not chiral, you don't have to worry about it. But what if it's like in a benzylic, but it's also in a secondary like this one? Then how would that change? For a benzylic and a secondary, within a acetylide ion, using ethyne here, since this is in a strong nuke, strong base, and that's in a benzylic and a secondary, and you do have a beta carbon that contains the proton this time. So I can make a double bond here. So this will indeed have a possibility of doing an SN2 and an E2. And if I have to pick one product out of those two, I would pick E2 as the major product, but certainly you can make both of them in there. So if I didn't really show any stereochemistry here, but if I was showing the stereochemistry, you want to make sure you invert the stereochemistry when you make the SN2 product. All right, so that would have been your SN2 product. And your E2 product would have been you remove the proton on the beta carbon and create the double bond there. So that would have been your E2 product. So for the E2 product, I would lose this hydrogen here. So I can have this acetylide here grabbing this proton here, and you have multiple hydrogens here. So you want to pick the one that's anti to the chlorine, and it doesn't really matter because it's not going to be having any stereochemistry on this double bond. So grabs this proton, creates the pi bond in there, and the chlorine leaves. That would have been your E2 mechanism. You can also use acetylides to open up the rings, like the epoxide rings. Because remember, the acetylide is in a strong nucleophile and in a strong base. So I want to use this as a nucleophile here. Since it's in a strong nucleophile, the question would be, where would it attack? So I can call these to be, let's say, number 1, number 2, 3, and 4 here. So between 1 and 2, which carbon would it really attack? So carbon 2 is more substituted, carbon 1 is less substituted, or you can say it's less hindered. So typically, if you're dealing with a strong nucleophile, the strong nucleophile kind of look for the electrophilic carbon that's going to be least sterically hindered, so which in this case is going to be carbon 1. And remember, whenever you use weak nucleophile in case of a ring opening of epoxides, you protonate that oxygen first before the weak nucleophile can go attack the more substituted site. So this would attack the less substituted site, so it will kind of go attack here. It doesn't a backside attack here, so it will invert the stereochemistry on that particular carbon. So I didn't really have the stereochemistry drawn here, but if there was an stereochemistry, then you gotta be careful with. You would not invert the stereochemistry of carbon number 2 because you're not doing anything, but on carbon 1 it gets flipped. So you make a new bond here, so anti to that O minus, and you have the C triple bond. Let's draw that with a straight line here, and a CH there. And then you can just do an acid workup or just water. So this would have been your first step, and your second step would be just water or dilute acid workup. And what that really does, it just puts the hydrogen back on that oxygen there. So if there wasn't a stereochemistry involved, however, so how would that change? For example, suppose I have this cyclopentane where I have this epoxide that's kind of coming out of the page like this, and then you have a methyl that's going back in the page here. So in the first step, I use acetylide here. So I know, based on the knowledge now, that the acetylide, since being in a strong nucleophile, is going to attack the least sterically hindered site, which is going to be carbon 1 here. So that does this backside attack here, and then this opens up. So now you can see how the stereochemistry on the top carbon would not really change at all. So I would leave that methyl going back in the page, and I would have this O minus kind of created. But on the bottom one, since it was doing a backside attack, it would have that ethyne kind of back in the page. Something like this. And then the second step would be just the workup step, and then dilute acid or even just water will do the job here. And all you're really doing here is just doing an acid-base reaction where you go ahead and protonate that oxygen now. Okay, so that's how you can use the acetylide to kind of do a lot of SN1, SN2. It's one of the common ways of kind of extending the rings. Like I can, suppose I have only 2 carbons in the acetylide here. I can make an alkyne that's going to be longer than 2 carbon just by simply running an SN2 mechanism. I just have to be careful with what type of alkyl halide are you picking in there, because you don't want to be picking secondary and a tertiary. For sure, never tertiary, but for the secondary, you get a mixture of products. So ideally speaking, you either want to pick primary or even a methyl halide. And you can also pick the benzylic halide because that would not be doing any sort of elimination reaction either.